Okay, so we will be starting our unit on equilibrium today. And since I'm not at school, I thought I'd try and make you a video and see how that works. So we'll give it a go. In most of our labs that we've done, our reactions generally go to completion or very close to it. We pick them that will go to completion just because it makes the lab work better and we get better, more meaningful data and things like that. But in the universe, most reactions don't make it to completion. They reach a point that we call dynamic equilibrium, which we will discuss in just a few minutes. So, for an example, as the reaction begins, the reactants are in contact with one another. So, for example, nitrogen gas and hydrogen gas might be in the container reacting together. Over time, our products will begin to form. And then at some point, those reactants will start to fall apart, or the products will begin to fall apart back into those reactants. I guess I should have done it this way. And then this situation called dynamic equilibrium occurs, and we write that with the double arrow. So it would be into 3H2. So we got nitrogen and hydrogen gases combining to form ammonia gas, and ammonia gas falling apart into nitrogen and hydrogen gases. And when that has established itself, when that dynamic equilibrium is established, the forward rate and the reverse rate are equal. Wow, what just happened to my line? The amounts or concentrations may or may not be equal. And even though it looks like the reaction might have stopped, the reaction does not stop. The reactants keep making products, the products keep making more reactants. So while the numbers of molecules of the reactants or products may remain the same, the actual atoms making up those molecules keep changing, and I've tried to draw that here using different colors. Notice how the purple-red combination became a purple-blue combination, and the green ended up picking up blue, and the two red circles became a double red circle. So it just, everything keeps changing. Even though the numbers of everything stay the same, which molecules they are keep changing. Dynamic means changing. In music, they have dynamics, which is how the volume generally changes. It goes louder or softer. And then equilibrium means the same. So everything's the same, but it keeps changing. So that's what is meant by dynamic equilibrium. So in the last unit, when we had an equation like this, if it was an elementary step in a mechanism, we would say something like the rate forward, and I'll put a little K1 and a K minus 1 up here. So the rate forward would be K1 into concentration H2 concentration cubed. It was elementary, so we go from the molecularity. And the reverse reaction rate would be K minus 1 and H3 squared. And then we might combine those things that since the rates were equal, that K1 into H2 cubed equals K minus 1 and H3 squared. And for those problems, we generally then solve for one or the other of the chemicals, putting all the K's together on the one side. So this goes without saying, the equilibrium, we're going to solve for K instead of for one or the other of the chemical compounds or molecules. So we'll combine the K's together, we'll combine the other things on the other side, and so we end up just from algebra. We get that situation if we're solving for the K over K. And in equilibrium, we change that K1 over K2 lowercase to a big capital K. And this becomes the format for the equilibrium expression, which is what we will come to call it. So in general, we've seen this equation before with the rates, but now for equilibrium with the capital K, it's C to the C, D to the D, over A to the A, and B to the B. Always do products on top, reactants on the bottom. And this, I believe, was what we call, I'm not sure, I haven't seen it in your book, but I haven't read it real closely, the law of mass action. So if you see that law of mass action, that just means to do this. And they may not even say it, so I don't know. It is what it's called. So how does this differ from kinetics? Well, it's a capital K, not a lowercase k. Both the reactants and the products are included in the expression, and the coefficients from the balanced equation are the superscripts on the different parts of the expression. You don't have to do an experiment to find out what those, we called those reaction orders before. I think I will pause right here, and that way I've got a better chance maybe of getting it to upload to YouTube. So I will pause, and then maybe I'll start the second video.